Yes, so yeah, we can hear you clearly. So if you are ready, sir, should we start?
Yeah, can we start? Yeah.
So let me introduce first. So I hope everyone is able to hear us. Can you use the chat box and confirm that you are able to hear us? Hello, participants. Yes, okay, thank you. So I welcome Dr. Harit Sahu, who is the scientist in the DRDO Delhi. He has already taken one lecture on the 1st September. So today he is talking, I think he's about to talk on the quantum teleportation theory and protocol. So sir, I'm now handing over to you. You can start your session now.
Okay. Thank you,
Thank you,
ma'am.
sir. Yes.
So let me share my screen. So is my entire screen is visible?
Yes, sir. Yes, sir, very clearly.
Okay. So good afternoon, everyone. So today we will be seeing the super dense coding, and we will be using this quantum entanglement for that super dense coding. So in that thing, first session we will be seeing what is this super dense coding problem is, and then how it is solved using some protocol, and how it can be implemented using a quantum circuit, and then we will be some example that how we can transfer 2 bits of information using only a single qubit in super dense coding protocol. Then we will have hands-on implementation of this super dense coding protocol on Qiskit. So before going to that, I just want to recap this important gates which we will be requiring every time during the session. So first is this Hadamard gate. So as you all know, this Hadamard gate, what it does is when you apply it on zero state, it creates superposition of 0 and 1, that is 0 plus 1 by root 2, and this is also called plus state. Same way we apply Hadamard on 1 qubit, then we get 0 minus 1 by root 2, and we denote this state as minus 1. Z gate when applied on 0 state, it will remain same. Z gate when it is applied on 1 state, it changes the sign of 1 state. And X gate just flip the bits. So X of 0 is 1 and X of 1 is 0, and it is denoted in quantum circuit by this plus notation. Okay. And there is this Bell state which we are using every time, and we call it as a 5 plus Bell state, and it is nothing but 1 by square root of 2 0 0 plus 1 1. And what is the property of this state is that either we will get both 0 0 or 1 1. One of them measures, then other qubit is also fixed at the same time. And this behavior of entanglement or this correlation, measuring same qubits, same output, is called entanglement. So it is exhibited by this Bell states, and it is one of the Bell state 5 plus which we will be using for implementation purpose. And there is another we called as control not gate. So what it does is it's a 2 qubit gate. It operates on 2 qubits. One is shown here, this A qubit, and there is other B qubit. Flip the qubit B by this notation of X gate. So the output of this gate is that A will remain same and B will be A XOR B. So whenever A is 1, it will flip the B qubit. So whenever A is 1, so A plus A XOR 1 is nothing but B prime. So whenever A is 1, it will flip this thing, otherwise it will remain same. And if you want to see it as a truth table kind of representation, then we can see that A and B can take 0 0 0 1 1 0 and 1 1 values, and when we apply this CNOT gate on this AB qubits, what we see is that A will remain same because it is control qubit. So in this case, this A will be same as the first column, so A will remain same, and B will change as per A XOR B. So just we are XORing A XOR B is 0, 0 XOR 1 is 1, 1 XOR 0 is 1, and 1 XOR 1 is 0. So what we are observing here is that whenever this control qubit A is 1 here, so it will change the B qubit. So it make it 1. Whenever this control qubit is 1, it will change this qubit to 0. So whenever this A is 1, it is flipping the B qubit or the target qubit. So 0 become 1, 1 become 0. These three gates we will be using, and this Bell state we will be using in our every this session and other session. So what is this super dense coding problem is? So in the last time we have gone through quantum teleportation. It is similar kind of thing, but the purpose of this super dense coding is different here. But the purpose is that Alice and Bob are there, and they are on different, they are distant away. So see here, Alice is here and Bob is here. Alice want to share two bits of information. So let's call them A and B. This information, this is classical A and B bits. Alice want to send to Bob, and that too using only one qubit, using only single qubit. So single qubit, if you know, single qubit is denoted by this thing, alpha times 0 plus beta times 1. So single qubit is like this, alpha times 0 plus beta times 1. But when we measure it, we will get either mod alpha square, we measure probability of measuring 0 is mod alpha square, and probability of measuring beta, 1 is mod beta square. So what we are trying to say here is that on measurement either we will get 0 or 1 with these probabilities, mod alpha square and mod beta square. So this psi is a state if we encode this alpha and beta in this, but at the receiver side on measurement, the receiver will get the information about one bit or alpha or beta only. So with this kind of psi state, we are not able to send both the A and B bits. So a single qubit state can deliver only one bit of information, either alpha or beta, although it is having both, but it will be collapsed to one of them. So how we can do it? So it was it can be done with a entangled pair of qubits 5 plus. Suppose if we have 5 plus with us, and we can give one qubit to Alice and one qubit to Bob, and Alice encode its bit value A and B into it, and then send this qubit to Bob, and Bob will do decoding of those bits and can recover both A and B at the receiver side. So we'll see with the protocol diagram. So the idea here is that Alice want to send two bits of information using a single qubit. So how we can do it? We can see in the protocol scheme here. So what we are saying is, so sender is nothing but Alice is our sender here, and so what is the here is that Alice want to send these two bits of information A and B to Bob, and it has only one qubit. We can do it with a Bell state pair. So how we can create a Bell state pair, which we have already, that just we initialize two bits with zeros and control node, we get 5 plus state here. You know this from last session, had initialize these two qubits with 0 0, then apply Hadamard, and then the control node we get 5 plus state. So 5 plus, you can see how it looks like is nothing but is this. So we can create this kind of Bell pair or the 5 plus state. So we can create it. Now what we are saying is that one part, this one qubit. So there are two qubits. Let's call it qubit 1 and qubit 2. So what we are saying is that this two qubits are there, and maybe they can be implemented by a photon or any other subatomic particle. Suppose it is implemented by a photon. So what we are saying is that this q1 photon or the qubit 1 is sent to Alice. This is to Alice, and this is to Bob. The qubit 2 is sent to Bob. These are entangled bit 5 plus is there. One qubit is sent to Alice, other qubit is sent to Bob. Now what we are seeing is that Alice can encode this 2 bit of information in this single qubit. that is part of this ball-state pair. What it does is, depending upon where, so suppose A and B are classical bits. So what values it can take? It can take 0, 0, 0, 1, 1, 0, and 1, 1. These four possible choices are there. So depending upon the value of A and B, it applies Z and control NOT gate on the qubit 1. So this is nothing but qubit 1, it is coming to Alice. So Alice will apply Z gate if A is 1. If A is equal to 1, then it will apply Z gate. If B is also 1, then it will apply X gate. If these A and B are 0, 0, then it will not apply these gates. So what Alice is doing is, depending upon the value of A and B, which she want to send to Bob, she will apply Z and X gate on her part of qubit 1. Then she will send this qubit to Bob. So what Alice is doing? Alice is encoding this 2-bit of information in the qubit 1 and sending this qubit to Bob. Once this Bob has the second this qubit also Q1 with him, what Bob does is, Bob does decoding, and this decoding is nothing but ball-state measurement, which we will see subsequently. But ultimately what Bob is doing is, Bob is applying, so here your qubit 1 and this is qubit 2. So Bob is applying a control NOT gate from qubit 1 to qubit 2. Okay, this control NOT from this to this. And on measurement, we are claiming that we will get classical bit A and B, which Alice wanted to send. This will be the same bits A and B which Alice desired to send to Bob. So the high level part is like this. First we create a ball pair here, and one qubit of that pair given to Alice and other qubit is given to Bob, and at Alice encodes classical bits A and B by applying this Z and X gate on her qubit, and then she send it to Bob. Bob also do this. Bob also apply the decoding of these bits by applying these two gates, control NOT gate and Hadamard gate. And on measurement, it is claimed that Bob will have A and B, which Alice wanted to send. So far so good. This thing is clear, everyone. If any doubt is there, then you can ask. I cannot see that the chat, but you can ask, or maybe I can see the chat. Yeah. Yeah. So first question is, how are prepared bell pair shared in terms of transmitter and receiver channel? So as I told, this two qubits can be implemented by photons also. So this qubit 1 Q1 is a photon, qubit 2 is a photon. So we can send these kind of photons to Alice, one photon to Alice. So initially we bring this photon together. Q1 and Q2 both photon are with us, and we apply these gates, and then the state of these photons are entangled. Basically their polarization is entangled, means the polarization will be, both the polarization will be high, vertical, or both the polarization will be horizontal. So we can use them to denote 0, 0 or 1, 1. So what we are saying is that photons are there, we entangle them on the property of their polarization. Okay, so either they will have vertical polarization or they will have horizontal polarization. Now we can take these photons away. So one photon we are giving to Alice and other photons we are giving to Bob. Okay, so it can be done with the photons kind of thing. How does Bob decide for which qubit gate to apply? Yeah, so that we will see when we will derive the expression throughout the steps of this protocol. So what we will be doing is, one by one we will process, and we will see that which gate will do the desired thing. So let's, yeah. So far so good. So we can implement this kind of super dense coding protocol by just a bell pair and applying this encoding and decoding. we can transmit with this one single qubit this 2 bit of information, and it is being decoded by the Bob at the receiver side. So the quantum circuit, or basically the high level implementation, looks like this. So this dot dot line denotes that upper part is with Alice, and lower part is with Bob. Okay. Now initially what is happening is 5 plus pair is created. So we can create this kind of pair. Okay. So suppose we have created it. Now one part of the qubit, so maybe it is with two qubits, Q1 and Q2. So one part qubit we are giving to Alice. Okay. The other part we are giving to Bob. Now, depending upon the value of A and B, A or B, we are applying the Z gate and X gate on this qubits Q1. So if A is 0, then Z is not applied. If B is 0, it is not applied. But when A and B are 1, then Z and X gate are applied on the first qubit. Then it is sent. So first initial state is that we are having this kind of pair. Then step 2 we are applying Z gate depending upon value of A. Then step 3 we are applying X gate on the qubit Q1 if B is 1, and step 3 we are sending it. So it is step 0, step 1, step 2, and step 3 we are sending it, and step 4 what we are doing is we are applying a control NOT gate from Q1 to Q2. So now this Q1 is sent to Bob. So Bob is in possession of both Q1 and Q2, which were earlier part of this Bell state, but Q1 has been modified. So what we are having is that Bob is having both Q1 and Q2. Now he is applying control NOT gate from qubit 1 to qubit 2. Then at step 5, so we are just calling those as S5 is step 5. We are applying the Hadamard gate on the qubit 1. And now what we are saying is we are having the A and B qubits here, and if you apply the measurement operator over here, then you will be receiving what? So you just apply measurement operation on this. So you will have classical bits A and B, which was sent by Alice. So this is high level working of the protocol. So what we are doing is just we are creating the pair initially, then we are applying the Z and X gate depending upon value of A and B, which Alice wanted to send. So it will work for all possible values of A and B. So depending upon A, B values, which can be 0, 0, 0, 1, 1, 0, and 1, 1, these gates will be applied. Then it is sent. Then C0 is applied at receiver side for the decoding of this A and B here. So Bob applies these two gates and measure. On measurement, it will have same A and B which Alice wanted to send. And see here. So initially you can create a pair and we can give this qubit 1 to Alice. Now Alice apply this operation and can again give this qubit to Bob. And then Bob can do the decoding. So let's understand this thing with an example, that will it work or not. So someone is asked in the query. So just again rewriting those things here. Step 0, what we are having is 5 plus we are having, that is nothing but this state A and B 0 and B is 1. Okay, so we are initializing, we want to send basically. So this part is Alice, is Bob. So this pair is there. So what is initially there, and let's call it as a qubit 1 and call it as a qubit 2. So initially at step 0, what we have, step 0 we have 5 plus, or the state is like this. So just simply I'm writing that 0, 0 plus 1, 1. Okay, now what we are doing is depending upon the value of A. So since on the first qubit, so see here, this is your first qubit Q1, this is your Q2, So at step one, step not qubit one. B, since B is one, we will be applying not gate on qubit. Not gate. Can I tell that what it will do? It will be the qubit one. So this 0 0 will become gate has been applied. In step 3, what we are doing is we are sending it. So simply send it. At step 4, we will be applying control node from qubit 1 to qubit 2. So if you remember from the initial slides, wherein this is first qubit, it is control qubit, and whenever it is 1, it will flip. Okay. Now focus on the step 5. Step 5, what we are doing is we are applying Hadamard gate on the first qubit. Hadamard gate on first qubit. So it will be 1. So what first it will become, so you will apply Hadamard gate on first qubit. So this 1 plus 0 is your first qubit. Now what I'm there will be minus sign here. This is the entire thing, and 1 is here. Okay. So what we did is just we apply the Hadamard gate on qubit 1, qubit 2. So just we separate out this qubit 1 and qubit 2. Now we applied the Hadamard gate on Q1. So we get this state. You can see here, this thing will cancel out. This is minus 1, this is plus 1. So what we will have, 1 by square root 2, 1 by square root 2 again common. So 1 by square root 2, 1 by square root 2 also be taken out. And it will be inside, it will be what? 1 times 0 plus 1 times 0. So it is twice of 0. And so this is square root 2 into square root 2 is nothing but 2. So it is cancelling out. So what we are left with? 0 and 1. And 0 and 1. And this is the information basically our A and B we wanted to send. So see here, what we did is we step by step derive the progression of this protocol, in which we start with the Bell state and then we apply. So since we wanted to send 0 1 A and B, so we apply only the X gate. So step 1 Z gate is not applied because A was 0. So this way we derived, and at the receiver we have shown that we will receive 0 1 only. Similarly, we can do it for 1 1 state also. So how we can do it? So maybe, yeah, so maybe we can do it again. So for 0 1 we have seen. So in this state what will happen? Just see here. So initially we are having this thing 1 1 and it is 1 by root 2. So since what we wanted to send we wanted to send. So what will X gate, Z gate. So Z gate, you remember, it changes from 1 to -1. So this is your first qubit. First, so applying Z gate on 0, it will remain same, but here it will come -1. So not get on first qubit. So what it will become? What we are doing is to it to Bob 1 and Q2, and you know this. Since this control 1, so it will flip target. Now on this side, this part is your Q1, this part is your Q2. Now again you are applying Hadamard on the first qubit. So on the first qubit you apply Hadamard. It will be minus 0 plus 1 by root 2, and then again this entire thing is here and 1 is outside. So if you 0 will be cancelling out, and what we have minus 1 and minus. So starting out here, and then you have this one. So this thing will cancel out 1 times of 1 and 1. So at this, what we are having is 1, yeah, 1 and 1. So as you know in the measurement, so when we measure this A qubit, although it is -1 and this B is +1, so when you measure it, what do you call this? So probability, but probability of mod. So when we do the measurement, we get this thing with some probability, and the probability will be amplitude mod square. So since the amplitude is -1, it will be again plus only. So what we are saying here is that we wanted to send 1 1, and we are observing -1 state and 1 state, and if you measure them to classical bits, they will be collapsing to 1 1 only. Okay, so this way we have seen that for 0 1 it is working, for 1 1 also it is working. The same way it will work for all other 0 0 and 0 1 state as well. So this will be the progression after these steps, different steps, and it is working for all. So Alice wanted to send AB as 0 0 0 1 1 0 and 1 1. This way the after steps of progression will happen, and on the fifth step measurement you will have, and they are the same as AB which we wanted to send. So this way we are able to implement the super dense coding protocol, in which our goal was what? Our goal was that we wanted to send this 2 bit of information using a single qubit. This single qubit Q1. We are able to send this 2 bit of information to Bob because we sent only 1 qubit to Bob. Bob is already in possession with another entangled qubit Q2, and it will apply some decoding thing, and it will have the A and B. So ultimately what is happening is that Alice is able to send 2 bit of information successfully using super dense coding. So the word super dense is like this, that we are able to densely put 2 bits of information in a single qubit and able to transfer or communicate to Bob. So it will work for all, the circuit will work for every A and B value. Okay, and keep this thing in mind, that initially the Q1 is with Alice and Q2 is with Bob. Alice does some encoding here and then send this to Bob. This qubit is sent to Bob. Bob does some decoding and then measure. So it will get the same output. So if you want to implement the quantum circuit, exact quantum circuit, how it will look, then the Qiskit quantum circuit will look like this. So what is this first part? The first part is creating entangled qubit pair 5 plus. So this will create a 5 plus state here. Depend and B value. If A is 1 and B is 1, then only we will apply Z and X gate. If this A and B are 0, then we will not apply those gates. So like in case of you want to send 0 bit of information, then you will not apply any of these two gates. Okay, so that is nothing but encoding part. It is what? Encoding part. So basically it is this thing only. Part is encoding, because encoding is done at Alice part only. So Alice is doing encoding in her qubit. These 2 bits of information by this X and Z gate. Now Alice will send this qubit to Bob, and this part is nothing but decoding part performed by Bob. And when Bob measures these 2 qubits, he will have A and B, which Alice wanted to send. Okay, so this way we can implement exactly how this protocol works. So before going to the implementation on Qiskit, I want to just clarify the what are the differences, key difference there in these two schemes. One is called quantum teleportation and super dense coding. So before highlighting the difference, so see here what we did is in super dense coding is with one qubit, goal was to send 2 bit of information, 2 bit information transfer. Okay, so in super dense coding, because entangled pair is there in both teleportation as well as super dense coding. So here goal is that using one qubit, 2 bit of information to be transferred. That has been achieved. In quantum teleportation, if you recall, an arbitrary state, single qubit state psi, we wanted to teleport from Alice to Bob. This we wanted to teleport to Bob. So what we did is one qubit state is transferred with the help of 2 bits of information. So this 2 bits M1 and M2, 2 bits of information is what is the 2 information classical bits does some measurement operations here and able to recreate psi state at Bob side. So here 2 bits of information are sent to get a single qubit state at Bob. The summary is like this. In teleportation, goal was to transfer a single qubit. So a arbitrary single qubit state has been sent using 2 bits of classical information. And in super dense, just opposite, we are able to transfer or transmit 2 bits of classical information using a single qubit. So these protocols are look similar, but the purpose is different and different way they work, and different applications are there. So let's try this thing on Qiskit. How we can implement this thing on Qiskit. So far any question is there, participants? Let me check the chat box. Yeah, yeah. So these 2 qubits are there. They can be transferred to Alice and Bob. means we can create bell pair and we can transmit, because these two photons, once we entangled according to their polarization, we can send them anywhere without distorting their state. If we are able to send, then it can be done. Why step 2 are represented A and B classical? Because why? Because the purpose of this protocol is to send two bits of information. These two bits A and B, Alice want to send. So these two bits are classical only. These two bits are classical only, which we wanted to send. So here we are saying then these two are classical bits. But depending upon their values, if this A and B are 1, then we will apply Z and X gate. Okay. So I think it is answered. Oh, voice issues there. Just a second. Let me, ma'am. Can any participant confirm that my voice is still breaking, or is it okay now? On the chat box, is it clear now? Earlier it was not clear for everyone. So seems for some of them are facing issue, but for rest other it is okay now. So yeah. So this quantum teleportation I have shown last time also. So I will show it again. Yes. So with quantum photonic circuit, it is possible. The voice is not completely audible. Yeah, just see this protocol. So the question is that how we conclude the value of A and B if we measure only Q2. So we are not measuring Q2, we are measuring both Q1 and Q2. See here, we are measuring both this Q1 and Q2, these two bits. So this was Q1, Q2, and this is Q1 and this is Q2. So we are measuring both Q1 and Q2. So Q1 will give us A, Q2 will give us B. Okay. So this question, but we are measuring both Q1 and we are able to tell about A and B. So this nodes issue is still lagging or it is not lagging? Chat box, is it working real time or it is lagging so much? Okay. What to repeat? Can you tell? Ithar Mulu. Okay. So I think, yeah. Super dense coding completely. You want to recap? Okay. So I will recap. Yeah. No problem. So in super dense coding, what we are doing is we wanted to send this two bit of classical information A and B to Bob. We are achieving this using a bell pair, and bell pairs one qubit is sent to Alice and one qubit is sent to Bob. So Alice embed or encode two bits of information A and B in Q1 by applying these two operations, and then send this Q1 to Bob. At the receiver side, Bob is having both Q1 and Q2 and apply these decoding steps by control NOT gate and Hadamard gate. And then on measurement of this Q1 and Q2, Bob will have A and B values, which Alice wanted to send. So through this protocol, we are able to send two bit of information using a single qubit Q1 to Bob. So I think I have recapped that thing. So any other more queries are there? Any other queries there? Then you can write. Notes taking time. Okay. So I will write slowly. Okay. Okay. Then let's move to Qiskit implementation of the super dense coding. And okay, some participant requested to show that quantum teleportation as well. So I will try to show that as well. So this was the quantum teleportation circuit implementation. Just so if you remember from this quantum teleportation circuit, it will look like this. So in quantum teleportation, what we do is Alice, they have an entangled pair or basically 5 plus state with them and one qubit of that. So this is qubit 1, this is qubit 2, and this is qubit 3. So Q2 and Q3 are part of Bell pair 5 plus, and Q1 is in a state psi which Alice wanted to send to Bob. So Alice does these operations and this measurement on her qubits M1 and M2 and then send this M1 M2 to Bob, and Bob applies the X and Z gate on her qubit on his qubit depending upon M1 and M2's value. So suppose this M1 and M2 are 1 1, then X and Z gate are applied, and on application of these gates Bob is having the same state which was initially with Alice psi. So we are showing the same protocol with this similar implementation. So what we are saying is that initially this Alice is having this is qubit 1 which is we are initialized with 1. So what we are doing is we are applying the NOT gate. So NOT gate will make it 1. So qubit 1 is 1 initially, and this is the Bell pair we have created. See here, this is the Bell pair we are creating, and these are the operation performed by Alice because Alice is having first and second qubit with her. Then she does this measurement. On measurement she will get these two classical bits of information. Depending upon those values, Bob will apply on his second qubit NOT and Z gate. After this, we are saying that Bob will also have 1. If initially it was 1, so Bob will also have 1. So in the result also we have shown that these 001 basically means that this Q1, Q2 are 00, but Q2, third qubit is 1. So see here, everywhere third qubit is 1. 1, 0 is the first and second qubit, and this is third qubit 1. So everywhere your third qubit is 1, which you wanted to send. So at the end, our goal was that Bob should have in third qubit one bit, state 1. Why? Because Alice wanted to send 1. So see here, we have made it 1. We wanted to send 1, and Bob is getting 1 at the third qubit. So we are not bothered about first two qubits, what they are. We are bothered that third qubit should be value 1. So let's start with 0, initialize with 0, then also it will work. So see there. So just I'm commenting that thing. So now what I'm saying is that we are initializing the qubit with 0 state. So just rerun it. So we are not applying a X gate here. So first qubit 0 is initialized with 0 only. And what we are expecting is at the end, the qubit third, this qubit basically 0, 1, 2, third qubit should have 0 state. So circuit will look similar. Just the qubit which we wanted to send here is that information 0 we wanted to send. And at the end, if you measure the results, so see here, first qubit is 0, 0, 0, 0 means first qubit 0, second qubit 0, third qubit is 0. Here also see 1, 0, 0. First qubit 1, second qubit 0, third qubit is what? 0. So everywhere, all the places, third qubit is 0, which we wanted to send. So we run this experiment 10,000 times. All the time, the third qubit which we wanted to have is 0, and it is 0. So what we have done is we have shown it for 0. We are able to successfully teleport 0 state. Same way we are able to teleport 1 state. It means we can send any arbitrary state. Since we can send 0 and 1 successfully, then we can send the 0 plus 1 superposition state also. So I think it is clear. Then we can move to super dense coding protocol. So any query is there in the teleportation part, then you can ask. Otherwise, I can move to teleportation part any query. Okay.
No, sir, no queries there.
Okay, perfect. Then let's just quickly go to the super dense coding protocol part. So just as you know that we are using this libraries required for our simulation to run. So understand what we are trying to do here is we are trying to simulate or run the protocol on a quantum computer. Okay, on a quantum computer or quantum simulator we are running this protocol, but actually they can be run with photons or any other kind of technology of quantum bits. Okay, so this is the function I have written to create bell pair. So as you remember that in a quantum circuit we are supplying these two qubits A and B. First we will apply Hedda mod on the first qubit, then control node CX basically from first qubit to second qubit. So what we will have, a bell pair we can create. Now what we want is that we want to send 2 bit of information. So suppose Alice wanted to send 00 bit of information. Then see during the encoding process, if you just see here, just I want to making them side by side so you can see the. Yeah. So Alice wanted to send A and B. So this is the information A and B here. So just see here, A and B we wanted to send. So these 2 bits of value we are inputting from the user. So what Alice wanted to send, so we are just encoding the part. So you remember from the encoding part, just see here. Yeah, just this diagram we can use as a reference. So this diagram is visible to everyone.
Yes, sir.
Yeah, perfect. Now the code I will also zoom for you guys. Control plus. Yeah. So what we are doing in this encoding part here, if you see here encoding, we need to apply Z and X gate depending upon value of A and B. Okay. So if your A and B are 00, then you need not to apply Z and X gate. If it is 10, okay. So 0 is your A and 1 is your B here. Okay. So since just under read from right to left here encoding. So 0 is your B, sorry, 0 is A and 1 is B. Okay. So it will apply X gate since B is 1. So this is the case here. So B is 1, A is 0. So you are not applying Z gate, you are applying only X gate. When it is 0, 1, you will be applying Z gate. Okay. And when it both are 1, you will apply both the gates. And we are just saying that if you input anything other than this values, because possible values for 2 bits are only these four: 00, 10, 01, and 11. Other value if you input, then we are saying that say invalid message. And the decoding part, if you remember here, just what we are doing is we are applying control not gate and Hadamard gate. So we are implementing the decoding function here with these two gates. So just you know that we require, so these three functions we have created: one to create bell pair for this, one to encode, and one to decode. So these three functions are there to create bell pair, to encode message, and to decode. Now let's start with the how many qubits we require. 2 qubits. So 2 qubits we are initializing in a quantum register QC, and then just we are creating bell pair first and then putting barrier. So see here the output. Bell pair is created by this Hadamard control node, and then we have put the barrier. So this part is done. Bell pair creation is done. Now what we are saying is that this Q0 is the first qubit, that is with Alice. So depending upon the value of, so bell pair is created, we are asking for input. So once we pass the inputs, it will create the encoding circuit, and then it will decode, and then we can measure. So let's run it, then we will be more clear with the things. So we are running it. Just a second. So the program is asking to supply bit value B and A. So suppose my B is 1, A is 0. So 1 0. So basically what I am trying to input is B is equal to 1, A is equal to 0. I am applying. So as we know that A is 0, so Z gate will not be applied. Only since B is 1, so X gate will be applied. Just do it. Then see here, bell pair creation has been done here, first part. Then in encoding, only X gate is applied. Why? Because B was 1, A was 0. And then this is the decoding part at Bob side, and this is measurement. So on measurement, we should have what? So just run it. So the circuit has been created, and we are running it here on air simulator. On running it 1000 times, so we are seeing almost 1000 times. What we are saying is 10 is an output. So state 10 we are getting, that is we intended to send. Okay, so the bit information we wanted to send was 10, and it is actually been received by or measured by Bob. So let's do with some other input value. This time we will apply 1 1. So in that case, what should happen? It should during the encoding process, Alice should apply both Z and X gate. So see here the circuit, Z and X both gate are applied, and just run it here. So what we are getting? We are getting 1 1 state. See here in the histogram also we will see. See here, 1000 times we are getting 1 1. So we need to run it 1000 times because we know that the answer is fixed only. So there is no randomness in this thing. Just run it one time also, you will get the similar outputs. So 1 1 we put and we run it. So one time we run and one time we are able to get 1 1. Okay. And if you want to run, so because what we have done here is that we have run this thing on air simulator here. Same thing you can do on actual quantum computers with this kind of uh, coding. Just you need to import some libraries, and then you just need to save your account details, and then you can run it. So very simple things, and this code will be submitted to IBM, and you will get the results back once the code is being run. And during this thing, because on actual quantum computers you have certain number of basic gates, so whatever code you have written in whatever gates you are using, it will be transpiled to the gates of native quantum computer on which you are submitting the job. So the same circuit is converted or transpiled to be run by the gates available on native quantum computer. So we can do that also. So any questions over there? I can take those questions and we can break for 5 minutes. Yeah. So the question is, third bit is classical. Sitarabulu, just a second. What is the third bit in the bell? This thing. In case of super dense coding, we are using only 2 qubits. But in case of teleportation, if you are talking, in teleportation we have 3 qubits. Okay. So there were 3 qubits, and in case of super dense coding, we have 2 qubits. Correct. So Lalit has written correct. So super dense coding, the encoding circuit changes according to the classical inputs that Alice wishes to share. Perfect. Lalit, perfectly. You understood perfectly. Yeah. In teleportation, we have 3 qubits. Just see here. This is the circuit for quantum teleportation in which we are having 3 qubits: Q1, Q2, and Q3. Q1 is the state, Q1 is having state psi which we wanted to teleport, and Q2 and Q3 are part of Bell state phi plus. So these three are qubits only. And at the Bob side, Bob perform these operations X and Z depending upon the values sent by Alice M1 and M2. It will apply these gates and then measure. So at this point, it will have correct or exact size status replicated at the Bob side, and then it will measure. Okay. So yeah. So but it is 2 qubit system, right? In case of super dense coding, we are working with 2 qubits only. Yes, Alice and Bob, A and B are on Alice only. So Alice wanted to send A and B. Yeah, Shashwat, your query is clear. Both A and B are classical bits and that are with Alice. Alice wanted to send to Bob. So I think I have answered every question that is there. Then we can have a break if any other question is there.
Yes, we can take the 5 minutes break, sir.
Yeah, then we can resume at 3
Yes.
5.
Yes, 3-5. Okay.
Yeah. So, ma'am, this lagging issues everyone is facing, or it's only particular user are facing?
Everyone, sir, everyone.
Or maybe the net issue at my side, it may be.
Yes,
So,
yes,
if this kind of issue are there, then you just call me on my number. You can take my number from Professor Mitharwal. And if such kind of issues there, then you just WhatsApp me on this thing, or maybe
okay,
just to
okay,
point me out. Huh? So that
okay.
what I will do is maybe I can check my connections.
Mhm.
Okay.
Okay,
Okay,
sir.
ma'am.